Okay, so a number of people have asked me how to answer question 8 on the maths worksheet that is entitled Significant Figures and Propagation of Errors. So in general, the question is asking us something about basically the tale of Archimedes. Archimedes was charged with trying to find out the composition of a material. And so here I give you some values for the volume of water displaced, and they're 14.08, 14.14, 14.05, 14.26 and 13.98, and we have 5 values. So the mean of this is adding them all up and dividing them by the value, which is 14.10 litres. Here you notice I have 2 decimal places, so I've added all of these up. I have 5, that's an absolute number, and so I'm going to end up with the same number of significant figures in my answer as I do in my question. The next one was the masses. We were given the masses of 232.6 and 232.0 and 232.9, 233.4 and 231.8. Again, there were 5 of these values, and so in this case we find that the mean mass is 232.5 kilograms. Now, the density of a material is given the Greek symbol rho, and the density of the material is equal to the mass divided by the volume. So in this case we have 232.5 divided by 14.10, and this has the density of 16.49. I have 4 significant figures in each part of my question. I have 4 in my answer, and the units are kilograms per litre. But a quirk of this is that the units are also grams per centimetre cubed. There are 1,000 centimetre cubed in a litre, and there are 1,000 grams in a kilogram. Therefore, the 2 factors cancel, so these units are perfectly interchangeable. At this point, I'm not going to show how to work out the standard deviation. We want the sample standard deviation because the sample is quite small, and I'm not going to show you how to work out the standard error. But for the volume, the sample standard deviation is equal to 0.11, and the sample standard error is equal to 0.05. And for the mass, the sample standard deviation is equal to 0.6, and the sample standard error is equal to 0.3. In this case, we have 2 values which have been multiplied or divided together, and so we're going to combine the errors. In the error in my density divided by my density is equal to the error in my volume divided by my volume, sorry, that's a bit of a sideways V, plus the error in my mass divided by my mass. And if we go on to work this out, we'll see that this is equal to, this gives us our density as 16.498 kilograms per centimetre cubed. So I'm going to take this density and move it on into the second part of the question. So I know my densities here, 16.49 grams per centimetre cubed is the density of my mixed material. The density of my gold, I'm going to give the symbol rho AU, and that is equal to 19.23. Sorry, I should have included the error on this. 19.23, and this is 4. And my density of my silver is equal to 10.5, and that has an uncertainty in the last figure of 2. Sorry, this of course is cubed. So now, the actual problem-solving part of the problem. The density of the material is a combination of the density of the gold multiplied by the proportion of the gold and the density of the silver multiplied by the proportion of silver. And I know overall the proportion of the materials has to add up to either 100% or 1. So I'm going to say that the proportion of gold, AU, I'm just going to call that X. And I'm going to call the proportion of silver 1 minus X. All this is doing is telling me that overall these two components make up all of my whole. That's the assumption I'm making. I'm assuming in this case that the goldsmith hasn't been mixing it with something else. So overall I have something which adds up to 1. And so what I'm going to do is I'm going to say the density of my material, of my mixed material, is equal to the proportion of gold multiplied by the density of gold plus the proportion of silver multiplied by the density of silver. Now, if I start to put some numbers into this, I see that 16.49 is equal to 19.23 X, and then I've got plus 1 minus X of 10.5. So 16.49 is equal to 19.23 X plus 10.5 minus 10.5 X. Or just rearranging this to make sure all of my X's are on one side and all of my numbers are on another, I end up with 6.0. So in this case, 16.49 minus 10.5, I'm going to keep the fewest number of decimal places. So 6.0 is equal to 8.7. Again, I keep the fewest number of decimal places, X. So my proportion of gold in my material is 0.69, or that can be written as 69%. Consequently, so it's 69% gold, that means it's 31% silver. Here I have 1 decimal place, but that means I only have 2 significant figures, so I only have 2 significant figures in my answer. Okay, now to work out the errors. We found that the density of the material is equal to 16.498. So this means that we have an uncertainty of 8 in this final number of 9. Now the trick to this is being able to break down the gold component of this and the silver component of this. So I'm just going to start off looking at the gold. And we know that the gold is made up of 2 terms that are multiplied by together. The fractional composition, which we don't know the error for, multiplied by the density of the gold. And this gives us this value here, which I'm just going to call rho. These 2 terms being multiplied together means that we need to use the fractional error equation. And so we know, if we do a little bit of rearranging, I'm trying to make X my unknown. So the density of our material divided by the density of gold is equal to my composition of my fraction. And so now I have an error equation that looks like 0.08. This is the density of my material divided by 16.49 plus the density of gold's uncertainty divided by the density of the gold. And this is equal to the uncertainty in my proportion divided by the proportion I have. If I work all of the maths through here, I actually find this error is very small, 0.005. This is smaller than the number of significant figures I have in my answer, so it needs to be rounded up. So this becomes 0.01. The reason I only have 2 significant figures here, of course, is because of the way I had to do that that equation where I substituted the x in. I ended up with only 2 significant figures here. If I were to repeat the same process for the silver, so this time for the silver, I have this time my density of my material divided by the density of my silver, giving me the proportion of x. So I have the error in the silver and the error in the material, giving me the error in the proportion divided by the proportion. And in this time, I find the error is slightly larger, but again is smaller than the number of significant figures I have been limited to. And so again, this rounds up. So what I find here is that my percentage of gold, or my composition of gold, is 0.69 and an uncertainty of 1 in that 9. And if I have my silver, I have 0.31 and an uncertainty of 1 in that. So really Archimedes' method was really quite rigorous in finding out not only that the material was indeed a mixture of materials, but the composition of each of them.